All right, let's jump right into this explainer. Look, whether you're gearing up for the ACI Shotcrete inspector exam or you're out there every single day doing QC on the job site, you know that the devil is absolutely in the details. Today, we're zooming in on the exact numbers, limits, and visual cues you really need to master. We're not just memorizing a list of facts here, we're building a solid inspection framework. It all boils down to this. What should you see? What are you actually seeing? And what action do you take when things don't line up?
Here is our roadmap for today. We're covering 1. Fibers, 2. Materials and proportions, 3. Equipment and air pressures, 4. Real-world scenarios, and finishing up with 5. Inspector takeaways.
Starting off with Section 1, Fibers, Macro versus Micro, and Understanding Reinforcement Types.
So let's talk about the precise mathematical line that separates different fibers. And hey, major exam alert here, 0.012. That is the dividing equivalent diameter in inches, or 0.3 millimeters, that completely separates macro fibers from microfibers. If it's larger than 0.012 inches, it's a macrofiber. Smaller, it's a microfiber. You've got to burn this number into your memory because it fundamentally changes how that material is going to perform on the wall.
Now, you might be wondering, why do we even care about that 0.012 diameter? Well, it's because these fibers do completely different jobs. Macrofibers, which are usually made of steel or a heavy synthetic, give you your structural post-cracking performance. Basically, after the cementitious matrix cracks, these fibers step up to continue transferring the load. That's why you'll constantly hear specs talking about residual strength, energy absorption, or toughness. Microfibers, on the other hand, are much finer. Their main job is to control plastic shrinkage cracking right at the beginning and provide specialized functions, like giving you fire-spalling resistance.
And that brings us to typical dosage ranges for wet process fiber-reinforced shotcrete. Just think about the massive variance here. Steel fibers, they can range anywhere from 20 to 100 pounds per cubic yard. Meanwhile, microsynthetics are just 1 to 4 pounds. But here is the absolutely critical inspector view. Do not, and I mean do not, treat these typical ranges as universal rules for your project. The approved mixture documents always control the actual project. Your specific job is to verify that what's getting dumped into the hopper matches the approved mix design perfectly.
Moving right along to Section 2, Materials and Proportions, let's get into the mix fundamentals.
Because listen, even the best fibers in the world won't save a mix that's built on bad fundamental ingredients. Time for another exam alert. We all know potable, drinkable water is the gold standard for mixing, no testing required. But what if you're stuck on a remote site and absolutely have to use another water source? Well, that source requires strict ASTM compliance. Specifically, the comparative mortar cube strength of that non-potable water has to reach at least 90% of the strength you'd get if you were using pure distilled water. If you catch unapproved water being pumped in from a local creek or pond, that is an immediate field problem that you have to stop.
Now, let's talk proportions, specifically for the dry mix process. It's fascinating how rebound significantly changes your ratio. Picture this. A traditional dry mix might be perfectly proportioned at 1 part cementitious material to 4 parts aggregate when it goes into the gun. But think about what actually happens on the wall. It can end up closer to a 1:2 ratio once it's in place. Why? Because a huge amount of that coarse aggregate just bounces right off the surface as rebound. As an inspector, it is absolutely crucial to understand that the mix entering the gun is not exactly the same mix that ends up staying on the wall.
Okay, Section 3, Equipment and Air Pressures. Let's look at system demands.
You really have to remember that wet mix and dry mix systems operate completely differently. In wet mix, the pump is doing the heavy lifting to move the concrete, so you mostly just need air at the nozzle to shape the spray, usually around 200 to 400 cubic feet per minute. But consider dry mix. Dry mix requires significantly more air because that compressed air is literally what's pushing the raw material through the entire hose. A 1-inch hose needs 350 CFM at 100 BSI, but if you bump up to a 2-inch hose, you jump all the way to 750 CFM. If your contractor sizes up their hose diameter but completely forgets to size up their compressor, you are going to run into some major velocity problems.
So, the key here is memorizing these system-dependent operational rules. Grab your pens. Here's another exam alert. For dry mix, your operating air pressure should never dip below 60 psi if you're running 100 feet or less of hose. On top of that, the dry mix water pressure at the nozzle has to be at least 15 psi higher than your nozzle air pressure so it actually injects properly. And what about wet mix? Well, you're generally looking for a typical nozzle slump of 2 to 4 inches. The job task analysis specifically calls out nozzle condition as an exam topic, and here is exactly why it matters. As an inspector, you've got to realize that even if a worn-out nozzle still technically spits out material, it is producing a much poorer spray pattern. It messes with the stream shape, the velocity, and how the water is distributed. A degraded spray pattern directly compromises the quality of your placement, which inevitably leads to poor compaction and those dreaded voids hiding behind the rebar.
Let's put this into practice. Section 4. Real-world scenarios. Going from observation to action.
All right, let's step out of the textbook and onto the job site to apply this framework with a couple of field scenarios. Imagine you're standing there observing a wet mix crew. They're shooting normally, the stream looks great, compaction is perfectly solid, but then a crew member activates the blowpipe to clear out some rebound. The exact second that blowpipe kicks on, the main nozzle stream instantly drops in velocity and the spray pattern just completely falls apart. So what should the inspector notice here? Why did that just happen?
Well, you've just spotted a classic field problem: shared air demand. The system simply doesn't have enough compressor capacity to power both the main nozzle and the blowpipe at the same exact time. The required action here is black and white. The crew cannot shoot and use the blowpipe simultaneously until they bring in a larger compressor. It's a fantastic reminder that you have to evaluate the equipment as one complete interconnected system.
Let's try a second scenario. A crew is really struggling to pump a fiber-reinforced mixture. The fibers have totally changed the rheology. The mix is getting super sticky and the line is noticeably pulsing. To supposedly fix it, a crew member grabs a hose and just starts dumping unauthorized water straight into the hopper. How are you handling this?
That is an absolute bad practice. Now, it's true that fibers can definitely change mixture rheology and make it harder to pump, but throwing unauthorized water into the mix is never, ever an acceptable solution. It completely wrecks the water-cementitious ratio and compromises the final structural strength of the concrete. As the inspector, you must step in and halt this immediately. The mix design and the approved admixtures are what control the pumpability, not some guy standing there with a water hose.
Wrapping things up with Section 5, Inspector Takeaways and our final review. Let's distill everything we've talked about today down into 3 core rules you need for the exam and for your daily site checks. Number 1, remember that 0.012-inch threshold. That's the magic dividing line separating structural macrofibers from shrinkage-controlling microfibers. Number 2, understand the fundamental air requirement differences. Wet mix requires way less air than dry mix simply because the pump is doing the heavy lifting. And number 3, you absolutely must evaluate the equipment and the mixture as a single, connected, living system. Which leads perfectly into your main field takeaway for today. If the Shotcrete stream visibly changes on the wall, do not just stare at the nozzleman's technique. Check the whole system. Look at the mixture, the air pressure, the water flow, the hose diameter, the pump, and even the physical wear and tear on the nozzle itself. That entire chain dictates the quality of the final product.
I really hope this explainer has sharpened your inspection skills and given you a much clearer lens for the job site. But our work isn't quite done yet. Now that you know exactly how the material properly gets to the wall, are you ready to spot the hidden defects inside the concrete before they compromise your entire structure? I will see you in the next lesson where we're going to tackle safety and visual core quality.